Alrighty, so I'm gonna, I think, follow the pattern I had this morning of sort of saying the same sort of things that the previous speaker said from a slightly different angle. Um, Aaron, of course, and I have talked about these kinds of things quite a bit, and it was interesting to hear his perspective on this laid out. Um, like most of my talks, this is going to follow a somewhat similar pattern, what we're doing now, what we'd like to do, constraints and scenarios. So this is really getting at, I think, a lot of the problem in terms of is about compute resources. And then I want to touch on, again, this is another place where multi-fit is disappearing. You'll notice there's nothing about how we're doing right now here. I think this is an area where, as you'll see, what we expect to do is so qualitatively different from how we're doing right now. I don't think it's a good use of everyone's time for me to try to go into that. I think it's also fair to say we haven't characterized it well enough for me to want to talk about how well we're doing right now. But what we're doing right now is really thinking of shear estimation as a full pipeline problem. And our work so far has really focused on making the earlier stages usable for downstream shape measurements. And this has been used for real shear estimation on real data in the HSC year 1 weak lensing results. And these involved integrating and actually forking PSFX so we could use it as a library rather than an executable and making it solve our problems. Actual fixes to some of the PSFX interpolation logic to work better on barely sampled images. HSC sometimes gets extraordinarily good seeing, and despite its small pixel scale, we're worried that the PSFs aren't really fully sampled. And that certainly theoretically means that a lot of stuff we're doing is just cannot be fully correct, but we can make it a little bit closer to correct and have. And then we've also spent a lot of work doing careful propagation of PSF models and the masking that affects them through coaddition, again, at the HSC scale. For the shape measurement itself, the thing that we apply to galaxies to get quantities that you can then turn in somehow to ensemble shears, we've got really two things, and none of them are adequate. The first one is we've pretty fully integrated the older Gaussian-based HSM algorithms. So these are including re-Gaussianization. These are moments-based methods. HSM stands for Harada, Sojak, Mandelbaum. Moments-based methods that correct the moments of galaxies using moments of shear, similar to KSB, which many of you may be more familiar with. And we also have sort of what I would consider a prototype or placeholder integration of NGMix and meta-collaboration that runs on our coads. This was co-developed with Desk, especially Aaron. We basically threw it together during a hack week. In terms of what we're doing right now, I think I'd say that our current pipelines control the systematics well enough for those of you familiar with the term, a dark energy task force stage 2 survey that specifies sort of a certain amount of data and a certain amount of systematics control that has to go with it in order to get everything you can out of that data, volume. And that was HSC at PDR1. HSC is generally a stage 3 survey, but there wasn't much data as of year 1, so I think this is where we're at right now. And the big caveat being that also required a major simulations-based calibration effort. The shear algorithm we used for that was re-Gaussianization, and that needs a large calibration factor of the type that Aaron just told us you really don't want to be making. LSSC is of course a stage 4 survey, and that's much more demanding. So we have a lot of work to do, and I think essentially everything on the last 2 slides will need to be improved or replaced, more of the latter, in time for DR1. So first off, going back to those first 2 slides, this work on PSFX, we basically plan to drop PSFX in favor of PIF. The people in the LSSC science collaborations, especially Desk, or perhaps exclusively Desk, are working on PIF instead. It's evolving rapidly and getting better and better. And Josh already said this, but we plan to adopt PIF, use its current mode as essentially our fallback option, and contribute code, primarily through Josh himself, to get our wavefront modeling ideas into that code base and use them that way. The propagation of PSF models, I think we've learned a lot from our current code. I think we've pushed the state of the art on this, and we've also learned enough about it to know that we have to change it significantly to manage the discontinuities better. And that's something I mostly talked about in my Tuesday talk on coads, and I'll bring up again a little bit later in this talk. For shape measurement itself, I think The Gotham HSM implementations aren't going anywhere. They'll stay in the stack. It's very useful to have something simple and fast for diagnostics. We may always use these for, PSF systematics, for instance, but this won't play a role in any sheer production pipeline for LSSD data releases. And this, I called this a placeholder for a reason. I think it's not really maintainable in its current form. Aaron's code is quickly evolving, and our code is quickly evolving. And right now, this code breaks anytime either of us evolves either of our code in a main way. So we need to rewrite this integration letter and be more careful about the software engineering behind it. So the theme here, I think, is that across the board in all of these different parts of the pipeline that are relevant for weak cleansing, DM has a placeholder working that corresponds to what the state of the art was 5 or maybe 10 years ago. But we've been contributing to the algorithm ideas that replace them, and we're working with desk members, in many cases, people you've already heard speak at this workshop, to implement those ideas in external code bases or integrate those code bases with the DM pipelines. This first point was probably a little bit unfair to our coads. I think our coads are not 5, 10 years old. They need to be improved further, but they are, I think, pretty close to the state of the art for making coads. And I think in terms of our contributions to algorithmic ideas, those have primarily been in co-addition and PSF modeling so far. In terms of actually integrating and working with desk members, I think I would say that this has not happened nearly as much as we need to. We've talked to a lot of people, and I think we're on the same page as a lot of desk people, but we've been understaffed in this area, and we've been focused on other problems. I think that's changing now. I'd like to wave hello to Arun Kanawati, who just joined the DM team and is someone who has a lot of experience in this, and we hope will be helping this effort going forward. I think it's worth now talking about DM's ideal shape measurement code. And this includes both sort of technical criteria from a science perspective and technical criteria from a computing perspective. What we would like to run for our data releases. I think we'd really like to use something that uses the same PSF models as the rest of our measurements. This is entirely compatible with the feedback loop that Aaron talked about of them working on something separate, that trying to use DM code and feeding their ideas back to us. We'd certainly like to use something that runs in the same coads as the rest of our measurements. And in fact, I'd say that having, at some level, weak cleansing requirements from Aaron et al. Can drive how we make our coads, because a lot of the other things we'll be using our coads for won't care about the extra details that weak cleansing needs. They won't be negatively affected by them. And so I think I'm pretty confident we'll be able to make sure that the coads we make are the ones that the shared algorithms can use. We'd also like to have shape measurement codes run on this, at least a subset of the same detections as the rest of our measurements. I'll come back to that in a bit. We'd like to run a code that's been battle tested at scale on a stage 3 survey and used for science. I think everyone who's done this before knows that you learn a lot by really trying to do it on real data, trying to do science with it. And while this may not be possible, in detail, because codes are always evolving, we'd like to have something that has a heritage of having been used for science, especially if we only get to run one shear code. We'd like to have something that processes more than 100 objects per second per core. I'll come back to that in a moment. And I think we need something that has compact output, something that reports a few numbers per object, not an enormous likelihood per object. So let's unpack this a bit. Something that's battle tested at scale in a stage 3 survey probably means it's not something developed inside DM. I don't think DM is planning to develop something that will be run on HSC or DES by the time LSSD needs to pick something and really go with it for DR1. NGMix and Medi-Cal is what we've been following most closely. We've certainly been following BFDM a little bit. I think I'm very excited about the possibility that BFD could work. It's something that I think has the potential to go quite fast, and that makes a lot of us breathe a sigh of relief. But there are other codes that are being developed, and we probably should be following those more than we are right now. I think I'll be very sad if we can't accomplish the goal of having shear codes run on our PSFs and coads, but I think we can make this happen. It just requires working with people that we already have been working with. The meta detection approach to blending makes this tricky. It means that you want to define a sample of objects that you measure that depends on an applied shear. And I don't want to get into the details of that, I think there are clever ways to get around this. Again, maybe along the lines of weak lensing wants something special in this department, and what it wants isn't going to negatively affect other science cases. So maybe we can just use what weak lensing wants everywhere. But I think we need to look into that more carefully. I also think it's true that nobody really knows how to do shear versus blending versus photometric redshifts at these depths. And meta detection is, I think, a very promising idea that, but there may still be other new qualitatively different promising ideas by the time we get on the sky. This speed number should be taken with a grain of salt. This is how fast something I think would need to go for me to feel confident in our compute budget or to consider running multiple shape codes. Slower codes may absolutely still be viable, and I'm not super optimistic we'll get anything that goes quite this fast. But as you've heard Fred say, as you've heard Dan say, as you've heard me say, there are a lot of components in our pipeline that are hungry for more compute resources, and there's going to be a lot of competition for our compute budget. So with these constraints and these criteria for what we'd like to do, I think there's a few scenarios. I think the ideal one is that there's multiple codes that meet or exceed our criteria, and we can afford to run them all, and we do that. And I think everybody would love to have multiple shear codes running so we can compare them against each other and learn from that experience. It's also possible, though, I think that we'll be resource constrained, that multiple codes might meet our criteria or, you know, more accurately, the science collaborations criteria, but we can only afford to run one. And I think we need to think about being able to make a high-level joint decision between the operations project and maybe at some level for DR1, the construction project, and the science collaborations, if we have to make a super high-level, you know, impactful choice on this question. A similar scenario is that there's technical trade-offs. None of the codes meet our criteria. You know, maybe one of them is fast enough, but wasn't run on a precursor survey in any form. But other one was and isn't fast enough. I think there's another decision point here. It's gonna, you know, unavoidably can be constrained to those that are fast enough for some value of what fast enough means. And I think there's a worst case here where nothing that the science collaborations think is good enough meets our criteria for fast enough, and we can't find ways to add new compute resources. I think we'll all work together and try to find more compute resources. We'll all work ways to find more, you know, creative solutions around this problem. Maybe it involves doing some of this processing not for every data release. But in the absolute worst case, I think it's DM's job to focus on the earlier steps of the pipeline, the PSFs, the coads, and run something fast enough and leave the next step of shares to the community. I don't know if we'll ever get to that point. I think with working together, we shouldn't, but there is a budget here. And that's really what I want to drive home on this point. We do have a compute budget. We don't know exactly what it is in terms of applying to individual algorithms, because again, there's a lot of competition for those algorithms. And it's possible we'll get to a point where there's a difficult trade-off between different science cases that each want to run something that's too slow to be run all together, but might individually be fast enough to run one at a time. And I think it's also true that the shape measurement code we will run, even for DR1, does not yet exist in anything like its final form. And we can't know yet what its resource needs will be. All we can do is work together to try to make sure that we can run something that we're satisfied with on the compute resources we'll have. It's also worth pointing out that DM doesn't really expect to play a production role in either running catalog space operations that transform uncalibrated per object estimators to calibrated ensemble shears. That was probably a difficult sentence to unpack unless you're a weak lenser. The basic idea is that you do some operations on the pixels, and that gives you some numbers in your catalog. And then to know whether those numbers are any good, you actually have to do catalog space operations on ensembles of objects to try to estimate shears from them. And you can't really know whether you've done a good job on the pixel space operations until you've tried to do those catalog space operations. But those catalog space operations are going to be primarily done by people using LSST catalogs, not by the DM team that's producing those catalogs. Whereas the pixel space operations are, we certainly hope, going to be done by the DM team running on DM compute resources. A related point is that you need major simulation campaigns, as Aaron mentioned, for shear calibration, or at least testing that simulation-based shear calibration is necessary or unnecessary. And these are things that I think are outside DM's scope, both construction DM and DM's final form and operations. We may do a small amount of both of these internally for initial validation, but I think we expect to rely very heavily on the science collaborations in practice, especially desk, for help in validating shape measurement algorithms. And I think this will require a really seamless relationship between the science collaborations, again, especially desk, and the ops project in validating data releases. And we need to make sure that we are not prohibited from doing what's scientifically necessary by having organizational boundaries between those groups. All right. At the end here, I'd like to talk a little bit about what we'd originally planned and why it's not what we currently plan to do. Many of DM's baseline documents were written around 2013. That makes sense. That's about when we went through FDR and started construction. And back then, a reasonable guess at what the state-of-the-art shear estimation would look like in 2020 was that you would Monte Carlo sample from the posterior of a PSF convolved galaxy model, computed jointly and simultaneously over all epochs. So let's unpack that a bit. We're fitting to all epochs simultaneously. This is the same thing I've said was, computationally expensive and computationally wasteful in previous talks. But we were also Monte Carlo sampling, not just fitting a maximum likelihood. And that was because back in 2013, I think there was the thought that the way that you would get around shear biases was that you could use that sampling of the full likelihood and a good choice of prior to make the biases go away at some level. And because we knew we were going to be resource constrained even then, we were hoping that you could get away with this with just 200 samples per galaxy. That number was the number we put in the documents. Number was driven entirely by compute resources, not by anyone demonstrating that you could do this with 200 samples per galaxy. And back then, I think we had not realized, I mean, we hadn't started processing the HSC data to the extent we have now, that blending was going to be such a huge problem. And this plan did not really think about how you would handle blending in shear estimation. So the first big change here is that we're not really planning to do that Monte Carlo sampling of the galaxy models. Nobody's asking for them today, as far as I know, and we no longer plan to produce them. I'm not sure that anyone was ever really asking for them. They were sort of a placeholder for what we thought the community would want in 2020. I think we will still absolutely do galaxy fitting for photometry, but with greedy optimizers, and that's more what I talked about this morning and what Dan talked about this morning. So changes to the DPDD are in the works. These have not been formally approved through all the LSST organization, but it's what the team that's doing the implementing on the ground has been thinking. We also don't plan to do the multi-epic fitting anymore. I've told you this before, I'm just repeating it again. That means that we have to do shear estimation on the coads. And I think that's what everyone actually has been talking about who's given talks on this. And there's a few points that I want to make on that. First off, the mathematics say the coads ought to be good enough. We think shape measurement on very careful coads can be proven to be good enough for DR1. I think we never had a coherent story for how to handle deblending multi-epic fitting. I think the blending problem is easier to handle on coads. And once again, the fitting on multiple epics is just prohibitively expensive. So the mathematics. First off, I'd like to remind everyone that the reason we all went towards, at least as I understand it, the reason we all went towards multi-epic fitting, a number of years ago, was because people had seen real problematic PSF systematics because they were trying to fit a continuous PSF model to coads that had been produced with a discontinuous PSF. So instead of propagating the PSF through like we are doing now, they were trying to fit a new PSF model using a continuous model to stars that did not represent a continuous PSF. That was solved years ago. I think G and Tyson were the first ones to really point it out. By propagating the PSFs through coaddition, we've implemented that. It mostly works. I've also talked about on Tuesday how with Kaiser or decorrelated coaddition, it's at least theoretically possible to avoid any signal noise loss. And I think there are the small scale demonstrations of that have borne that out. But more importantly, I think the measured signal noise loss from direct coaddition have been negligible in practice, at least for this purpose. Now that's all nice, but I certainly would expect you to ask me to prove it. And I can't do that yet, but I think we're on the road to doing that. First off, the DLS, the Deep Lens Survey, and the HSC Year 1 shear catalogs were built from coads. Neither of those is anywhere near the level of systematics control we need for LSST, but I think they are good first steps. The other thing that many of you may not be aware of is that there's been a long-running simulation project involving both DM and desk members. This has been read by Bob Armstrong and Aaron Sheldon. And this is shown, I'm previewing this a bit, that shear estimation on coeds is viable for both Medi-Cal and BFT. But you have to be very careful to resample the PSFs in exactly the same way as the images, what Aaron talked about a little bit in the last talk. The paper for this is in prep. My understanding, Des people on the line can correct me if I'm wrong about this, but my understanding is that Des Euro6 processing will at least be attempting to do shear shape measurement on the coads. I think they're running other things as a fallback option as well. And I'm certainly hoping that the results of that when it comes out will be a nice demonstration of the advantages and possible pitfalls of trying to do shear on coads. Really looking forward to that. All right, so where does that leave us? I think first off, I'd say the lack of shear estimation sophistication in our current pipelines should not be taken as an indicator of a future lack of sophistication. There's a lot of work going on behind the scenes that has not made it into the master branch of the code that we run every day, including work by us. But there's a lot more work to do. And a lot of that involves working with many of you in the audience. And I think it may involve some hard choices. And I'd certainly like those of you in the audience who play major sort of organizational roles to think about how we can break down the barriers between organizations that have to exist as separate entities and operations and make sure we can make decisions together. However, with all those hard sources, I would not expect Multiepic to be one of those choices. I realize we haven't proven that yet. I think we will. Certainly find me right now if you're unconvinced by the math that says we can use coads. I think I can make a pretty strong case there. I think stay tuned if you want more than the math, which I think would be entirely reasonable at this point. Thanks. That's it for me.
Okay, thank you, Jim. Let's thank Jim with a round of virtual applause. We have some questions lined up. Okay, Michael, go ahead.
Hi, Jim. I had several questions. One's a technical. How many of the different algorithms are actually doing mathematically, or building some of the same mathematical building blocks in terms of array and matrix operations and such, that you could reduce the compute load? It's largely a technical question, but it's kind of an interesting one for this audience. The second, though, is more, do you actually think the ultimate limitation is compute resources or providing clear products to people?
Oh, well, I mean, I think they're both challenging problems. I guess it's easier for me to see a problem with the compute resources coming, you know, at me in a scary way. It's the problems with the data products, I think are entirely likely, but they're more unknown kinds of things, and it's hard for me to talk about them coherently right now. Maybe
and then the third, go ahead.
Sorry, go ahead.
I was gonna say the third question was, you're making a number of useful declarative statements, what will be done and not done. But it seems like really the question is, when will certain things be done or not done, right? Because what you do in year 1, 3, and 10 may all be very different. What you do in a DDF versus the wide fast deep. Like in wide fast deep in year 1, a lot of discussions of how you make coads or edge-free coads, like I don't think you can, right? So, aren't nearly the same as when you have 10 years of data.
Yeah,
and so we're having this discussion about what we're doing, what's going to be ready for ORR, you know, at the end of the construction versus what's going to be in DR1, DR2 versus what's going to be in DR5.
Yeah.
6.
So I'm certainly much more confident about us getting a handle on these problems a few DRs into the survey. I think, you know, the history of shear estimation is that nobody has gotten it right for the new data volume they're just now experiencing right off the bat. But everybody's figured it out as they've gone in. And the other side of that is that it's required the people doing the science to work really, really closely, in many cases, be the same people working on the lower level pipelines. And I am worried that LSST organizationally is not set up to repeat that success story. And I think we need to make sure that we avoid that particular pitfall.
Thank you.
Oh, I'm not sure I answered your first question, but I also forgot it. Could you repeat it?
about it might be useful and interesting for someone really smart. I'll nominate Gary to think about which of these different methods are actually doing some of the same mathematical operations for significant speed ups when doing joint processing of different algorithms or approaches.
I do think a lot of it is just building the coads and evaluating the PSF models. I mean, if you get that part right, that's a lot. Well, that's a lot of compute time we've basically already intended to not have to worry about being split across different algorithms. There may be more than that, but I'd be a little bit skeptical if there were. Maybe just in Fourier transforms.
So you discussed the idea of having maybe several pipelines running for shear measurement, and I just want to make the point that it's, as long as these methods need calibration of simulations, then you're limited by your simulations. And so making lots of different pipelines that calibrate against the same simulations doesn't add as much information as you might think it does.
Sorry, Jim.
I have a bad habit of muting myself when I'm not talking, but that's a very good point. And it's not one I've been thinking about. I do think the DES people have learned from having multiple shear measurements running in previous data releases. I'd be interested to get some of their comments on that. I don't actually know if they had different simulation efforts for each of them.
So we have a question, another question now from Andrew Bradshaw, who I'm trying to unmute.
Hi, yeah, I was just wondering what the plans were for how to choose the algorithm that perhaps shear will be calculated with. If it'll be simulations or on real data, or
I think this is a
a
fair bit above my head, and I think it needs a procedure to be worked out for doing it. Now, I'm hoping that in practice, all the people involved in the decision at the technical level already basically agree and see which way the wind is blowing and have been working on the same things for a while. And it's more a question of, we've got these couple of options and we'll run as many of them as we can afford to. But I guess I take this as an opportunity to invite the desk leadership and project leadership of construction operations to think about how we would make such a decision if there was ever a contentious one.
Okay, do we have any more questions? Okay, well, let's thank Jim again for that presentation.